Okay, ji, Bismillahirrahmanirrahim. Let's start with the second portion of our first introductory lecture. Uh, and I think we have to start from formal proofs. So, this is formal proofs, and first we have to look over these deductive proofs. So, deductive means something that you have to extract or simply deduct, which is a verb. So, in these deductive proofs, you will be given with a given statement, and then you have to conclude a conclusive statement, a statement that we have to prove. So there are two parts. One part, something is given to you, and then you have to prove by taking that given statement, and then you have to do some process, and then you have to reach at the conclusive statement. So this is the sequence structure of the deductive proofs. And the step which is involved between these two uh, entities, given statement and conclusive statements, is the logical progression or the logical process. It's called logical because you have to oh, go step by step with some mathematical logic. You don't have to narrate things in theory, but you have to support your proof with the help of some mathematical statements. So that's why it's written as logical progression by direct implication. For example, if you have a statement like this one, if y greater than or equal to 4, uh, you can suppose that y is some number or whatever. Some statements will be given to you. Here it is not written, but we will see these things in detail here in next example. But for the moment, so you will be given with this statement. If y greater than or equal to 4, then we have to prove 2 raised power y greater than or equal to y square. So this will be given to you, and then you have to prove this conclusive statement that is on your right hand side. So how we can do this? We can see this thing here. So first we are uh, supposing, or we are introducing a claim that this is the claim of the problem, that if y greater than or equal to 4, then 2 raised, we have to prove 2 raised power y greater than or equal to y square. So for this, we have to suppose some number, because here y is given to us, but we don't know what this y is. So we suppose let x be any number, any number. We don't know what is the actual kind of that number, but it is an any number. And we can obtain that number by adding the squares of four positive integers. So which means that we can take four positive integers, then we have to calculate the square of each, and then we have to sum up all these results, and the number that we will get, or the number that we will obtain finally, will be the x. So this is our supposition. And our claim 2 is, so now x is given to us, the x that we have supposed here, and we are assuming that claim 1, which is this one, claim 1 is true. So we are assuming that claim 1 is true, and we are given with with a number x, which is a positive number again. So now we have to prove what? We have to prove 2 raised power x greater than or equal to x square, which is this, which is equivalent to this right hand side in our given problem. So let's start the proof. So given is what? Given is x. And x is what kind of a number? It is a positive number, which is a sum of squares of all the four given positive integers. So suppose a, b, c, and d are four positive integers. Then we have to square each of the given positive integer, and then we have to sum it up. and then the result that we will get will be a number that is called x. So this is according to this statement, the statement that we have uh, supposed in the beginning. So now number two, we know that this a, b and c are positive numbers, and if these are positive numbers then it means that they are greater than or equal to 1, because 1 is the least positive integer, then 2, 3, 4, 5, and so on. So okay, so that's why we are writing it here, that a is greater than or equal to 1, b is greater than or equal to 1, c is greater than or equal to 1, and d is greater than or equal to 1. So this is the minimum positive integer that can be positive integer value that can be given to these variables a, b, c, and d. But we have mentioned here that it is equivalent to 1 or it would be greater than 1, which means 2, 3, 4, 5, and so on. So what we can do next? Now we know that if we will take a square of these each number, then the square would again be greater than or equal to 1. If the value of a is 1, and if you take the square of 1 is again 1. Or if you will take the value 2, the square of 2 would be 4. So it would be again greater than 1. So the value of these all positive integers, if we will take the squares, then the square would be greater than or equal to 1. So this is the condition for all the things. And we are doing this by 2, using the equation in 2, you can say. So if these are the square values, then you can sum up these values. So we have one value for each positive integer, and then after adding it up, we will get 1 plus 1 plus 1 plus 1, which means, for example, x is equal to, which means what I am saying, x is equal to a plus b square, you can write, plus c square plus d square. Maybe you are seeing or not, I don't know, but I will try my best to display it. And now we have that, we know that this a is 1, so a square of 1 is 1. Similarly, b is 1, c is 1, similarly d is 1, which is equal to 4. So if we will get this minimum value 111, then it would be 4. But if you will get these values like uh, 2, I don't, if I will get the value for A2, then it would be 4. Similarly for B, it would be 4. Similarly for this one, it would be 4. Similarly for this one, it would be 4. And it would be 16, which is, so at one point we are getting 16. In previous step, we have obtained the value 4. So this 4, so we can write that x greater than or equal to 4. So if equal to 4, then it would be like this. And if you give some higher value, then we are assured that it would be greater than this 4, which is a minimum value. So that's why on your screens, so that's why on your screens you have written this thing like x greater than or equal to 4. So x is a number which would be greater than or equal to 4, and you can also conclude this thing by using this equation 1 and 3, because in 3 we have mentioned the minimum value, and in 1 we have mentioned the format how you can calculate the number x. So by using 1 and 3, you can conclude that x is always greater than or equal to 4. Now this is something equivalent to your left hand side. And now you can write that I can use this claim 1 when I have obtained the left hand side. Then you can say that I can use the claim 1, because now my x is very much clear. So now by using the claim 1, which I have supposed that it is true. Here I have supposed that claim 1 is true, and if it is true, then I can write that it is equivalent to 2 raised power x greater than or equal to x square by using 4 and claim 1. By using 4 and claim 1. So in this way, and you can see that these are the mathematical steps, and by using these mathematical steps in progression, you can deduct some proof for a given statement, and then you can reach at your conclusive statement. This is my conclusive statement, and this is my given statement. So in this way you can do these deductive proofs. And now in the next slides we have to differentiate theorems, lemmas, and corollaries. So theorem is something, a bigger thing. Lemma is something in between, and corollaries is a small thing. And all these things are related to some mathematical analysis. So, so generally, theorem is something called a major result. Theorem is something in which you have to calculate some, or you have to analyze uh, some complex and major things, major results. So the result word is very much generic, and it has uh, complete semantics actually. And lemma is what? Lemma is something, an intermediate result, and lemma normally used to prove a theorem. So you can use a lemma to prove a theorem. For example, maybe you are uh, conducting a proof for a theorem, and during that discussion, maybe you can introduce some lemma which will use some other theorem to prove this theorem that I am talking about. So this is something lemma. So similarly, the corollary is something, a small definition, you can say, small result, you can say, that you can use to again prove the theorem, or lemmas also you can use. So corollary can be used to prove a theorem or lemma, but in a very short definition. So now, for example, here we have a tree, and we can say that, and we know these things already through our data structures. So this is a binary tree, and this is an example of a theorem that the height of an n node binary tree. So this is something, I don't know what is the number of n. Here in this example, the number of n is, the n has a value 7 because 4 nodes and the upper 3 nodes 7. So 7 nodes. So the height of a 7 node binary tree is at least, and then you can use this formula, floor log of n. Floor is something, value, for example, if you are calculating 3 point, if you have the value, fractional value 3.5, what is the floor of that value? Only 3. And what is the ceiling value of this function? 4. So this is something I know you already know. So the height of this 7n node binary tree, what would be the height actually, by the way? So you can put 7 here in place of n. So log of 7 might be 2.8, and then taking floor, you will get 2. So the height of this tree is, this is 0th level, this is something level 2, level 1 and level 2. So the height of this tree is 2. You can get this value from this statement, which is basically a theorem, and it contains a detailed calculation. Similarly, this is the example of lemma, and this is the statement, level I of the perfect binary tree. This is perfect and binary tree. So level I, uh, level I of a perfect binary tree has 2 raised power I nodes. So this statement is saying that using this lemma, you can calculate the number of nodes at any level in any perfect binary tree. So this is perfect binary tree, and I want to calculate the number of nodes at level 1, you can say. So you can put this level number here. So I want to calculate at level number 1. So 2 raised power 1. 2 raised power 1, I will get 2. So 2 nodes at that level. And similarly, at level 2, you can put the value of 2 here in place of this I, 2 raised power 2, then I will get 4 nodes at that level. So this is an example of lemma. Similarly, corollary, a perfect binary tree of height h, whatever the height is. You can calculate the total number of nodes of that perfect binary tree using this formula, 2 raised power h plus 1 minus 1. So here I have the height, how much? 2, which I calculated here in first theorem. So I can calculate the height of the binary tree first by using this formula, and then you can put it anyhow. So height is 2. 2 plus 1, 3. So 2 raised power 3 is now 2 to the 4, 8. 8 minus 1 is 7 then. So 7 is the number of nodes that you will get by using this corollary. So these are the examples of theorem, lemma, and corollary. And okay, let's move on to the next slide. And it is a very simple slide, as it is the part of your introduction lecture about theory of computation. So it is quite possible that you will see these notations in your theorem, lemmas, or corollary. So, and you already know this from your course of discrete structures. So there is a symbol for every. This is, which is, you can say, the uh, capital A in reverse direction. Um, so this is a symbol for all, to represent for all or for every, and these are the universal. We normally use these symbols for universal proofs, and this is the notation. And we can also use another symbol, which is E. The you I don't know, maybe the mirror image of E. So there exists. We have this small phrase as a part of different theoretical statements. It can come in different theoretical statements. So we can represent there exist with this notation. And we have a concept of implication that we already studied in discrete structure, and we can represent that implication with an arrow from towards from left to right or from right to left, whatever it is. And in theory, you can represent this arrow with if some variable, then some variable. So here, for example, if A then B, so we can represent it with A implies A arrow B, or A implies B. So this is something already you know. And then the topic of formal proof is still going on, and there are 3 other terms that might be you will have to use in future. So there are some proofs that you can prove by contradiction. There are some proofs that you can prove by induction or by contra positive statement at the end. So um, how you can prove different things by contradiction? So contradicting from your original statement in simple definitions. So we have to, if we want to prove something, then we have to start with the statement contradictory to the given statement, which means if some statement is given to do and you have to prove something over this given statement, then how you can prove by using this contradiction method? You have to take a supposition. Supposition is a statement, you can say, but your supposition should be contradictory or a contradictory statement to the given statement. So we For example, when you are given with some problem, then some given statement would be there. So you have to take that statement and you have to produce a contradictory statement or an opposite statement of that given statement, and then you have to take that opposite statement and you have to start your proof. For example, here, to prove A implies B, we start with A and negation B. So this you can see, for example, this is something uh, a mathematical illustration of this proof by contradictions. So if A implies B is given something to you, then you have to start with A and negation B, and then show that could never happen. Okay. Similarly, induction, this is a very much popular method of mathematical induction in which you have three steps: the basis, the inductive hypothesis, and the inductive step. Um, it's only a reminder. In basis, you have to suppose something with, you can say k is equal to 0 or something like that, and then in inductive hypothesis you have to prove something with respect to k is equal to 1, and in inductive step you have to prove something with k greater than or equal to 1 for all values greater than or equal to 1. So you can see these things in, you already have seen these things in discrete structure, but these are the three steps involved in that induction proof. And finally is by contra positive statement, which is again uh, partially similar to contradiction. For example, if A then B, you have to prove something like that, then you don't have to start with that one. You have to start like this. If negation B, then negation A. So you are again going towards the opposite direction, uh, but in this way. You have to start with negation B, and then you have to reach at negation A. So this is an example of a contrapositive statement. I can go into detail, but this is not exactly the part of this theory of automata, so that's why I am leaving these things for you, because you already have done these things in your course of discrete structures. So, and then counter example. uh, any theory in the world can be disproved if you have a single example against those theories. Single example. So in literature, whatever the different theorems or theories or lemmas or corollaries are available, if you have an example to negate those theories, then you can come up with that example and you can negate that theory. This is called counter example, by counter example. Prove or disapprove something by counter example. But it does not mean that you can come up with some single example or maybe two or three different similar examples, and then you can say that, hey, look over it, and this is something I proved for 4 or 5 values, and then you can keep on doing like this. And okay, by taking these 3 4 values, now I can say that uh, something is proved. No, for proving for proving counter example is not enough. Simply what I want to say, counter example is used only for disproving or negating something. For proving something, counter example is not a method. You have to come up with proper steps and some proper methods that you have already seen, like for example contrapositive induction or contradiction or like this thing. Now, different ways of saying the same thing. These are very much fundamental things that you already have seen in the in other courses like discrete structures. So here on this slide, this slide is saying that, for example, if you have a statement like this one, if H then C, which is H implies C, you can say, then you can rephrase it as H implies C. Or you can write these two statements as H arrow C or H implies C. Or you can also rephrase it C if H. This is the only form in which the order is changed. C is on the left side and H is on the right side. Rest of the different notations representing H on the left hand side and C on the right hand side. And similarly, so what this slide is saying, that all these six statements saying the same thing. So these statements are not different from each other. They are the same thing. So now it's up to you to use which uh, statement, or which statement do you like the most. You can use that format. So this is for simple implication. And now for both directional implication, which we know that it is a form of if and only if statements. If and only if state. We can represent if and only if with I double F, this one. For example, if A, if and only if B, you can represent it with A double arrow, arrow on both sides, and then B. This if and only if contains two parts, the if part and the only part. So if part can be represented, if you look over previous slide, so this is the if part. And when there is a if part, C comes here on the left side and H comes here on the right hand side. So similarly, if part, what is the if part? If B then A. For example, if you have if B then A, so this is something if part. So this is written according to this format. This is the F part, and you have the things like that one. Okay, and the notation for this one is arrow in reverse direction, and the second portion is only if part, and only if part. If you look over here, it is very much similar to H only if, very much similar to the first one. So okay, A only if B, A only if B, and the representation or the notation for for this statement is arrow towards the right hand side, and it is very much similar to if A and then B. This is something we know that this is equivalent to if H then C, so that's why it is written here same as if A and then B. So this is same, these two things are same. Abbreviation, we know that IFF is the abbreviation, and you have seen this if and only if in different statements. For example, this is the statement of a theorem: let x be a real number, then floor of x is equal to ceiling of x, if and only if this is underlined. So this is the usage of if and only if here in this statement. X is an integer. If x would be an integer, which means the complete number, then the floor and ceiling of that integer would be equal. So anyhow, this example is only illustrating that, illustrating or giving the evidence that here you can use if and only if. And if you want to prove it, then you have to prove two things. Number one, the if part, and then the second part of the proof would be only if part. So you have to prove two things. So if there is a double implication in your given problem, then you have to prove two things. Keep this thing in your mind. First one is about if statement, and then the second one is about only if. Okay, this is something mentioned here, and now this is the summary of our first introductory lecture, uh, which was the introduction about different terms that can come in our course. So automata theory and historical perspective, we have seen Chomsky hierarchy, We have seen these things, finite automata, proofs, and now at the end, I said that read the chapter one for more example and exercises. If you want to do some um, practice, then the exercise is available in the book, and some more examples are also available in the book. You can read those examples and exercises just to make you a little bit warm up for this course. So thank you very much. And now I will proceed properly um, in the next lecture with my own notes. Thank you very much.